Hello and welcome back, fellow path integrators. Today with a very special video because first of all I would like to thank you guys so much for 1000 subscribers. Man, I really cannot believe it, how much support you guys have been giving me. So thank you very much. I really hope that you will enjoy my videos as much in the future as you do now, or even more. I want you to enjoy them more, I want you to learn more, I want to share even cooler things with you. So let's go, shall we? And I have a very cool integral today, as you can see. So it's a double integral over an area which is D, which is like the set of pairs x, y in the r squared plane, with the feature that x squared plus y squared is smaller than 2. So basically what we're doing is we're integrating over a circle with the radius 2. So we have a very fancy function here, arctan of x minus y divided by x plus y, and what we're gonna do is we try to get rid of this x minus y divided by x plus y, transform it somehow into a tangent, because then we would get rid of the arctan and the integral will get much easier. So what we will do is we will perform a change of coordinates, and our change of coordinates will look like this. So our x coordinate will be s times cosine of t plus sine of t, and our y coordinate will be s times cosine of t minus sine of t. And if we plug that into this argument of the arctan, then we will get that x minus y divided by x plus y is s times, so we can extract that, and we have cosine of t plus sine of t minus, and then y is cosine of t, and then plus sine of t, and the whole thing divided by x is s being extracted, cosine of t plus sine of t, and then plus cosine of t plus, not plus here, minus sine of t. So we have here cosine minus cosine on the numerator, so that thing cancels each other out. We have two sines here, so we get like 2s sine of t divided by, and then here we have the sine, they cancel each other out, and we have two cosines, so we have 2s divided by cosine of t. So the whole thing is tangents of t. So you can see if we plug that in with that change of coordinates into our arctan, then the whole integral will simplify enormously. But since we're performing a change of coordinates, we of course have to calculate the Jacobian determinant. So first take a look at how does the Jacobian matrix actually look like in our case. So first we take the derivative of x with respect to s, and we take the derivative of x with respect to t, and in the second row we take the derivative of y with respect to s and the derivative of y with respect to t. So if we plug that in, like if we plug our formulas in, then we have the derivative of x, which is s times cosine t plus sine t, up here. So the derivative of cosine is minus sine, the derivative of sine is cosine. So what we will get here is when we that is the derivative with respect to t, so that will come here. So we will have in this point s times minus sine of t and then plus cosine of t. And now we can take a look at this part here where we take the derivative with respect to s, which means that we will just stay with cosine of t plus sine of t in this cell of the matrix. Alright, so let's go to the second row. We will have to take a look at y. So now we do it the right way, so the right order. First take the derivative of y with respect to s. So as we will see, we will just remain with the cosine of t minus a sine of t, and now we take the derivative of y with respect to t, and what we will get is minus cosine of t minus sine of t minus cosine of t. So here we will have s times minus sine of t minus cosine of t. So this is our matrix, our Jacobian matrix. Now we have to take the determinant, we have to calculate the determinant of this matrix. So that's kind of easy because we just need to multiply the diagonal elements with each other and then subtract them. So what we have is cosine of t plus sine of t multiplied. So here we have an s, we can extract it with minus sine of t minus cosine of t, and then we subtract s times, now we take those diagonal elements here, so we have minus sine of t plus cosine of t, and the whole thing multiplied times cosine of t minus sine of t. Alright, looks good so far. What we are doing now is we just multiply everything out, and what we will get is minus s times brackets open. So we will have a cosine squared of t plus a sine squared of t. Then we will get a 2 sine I forgot the argument, t, 2 sine t cosine t. That's a thing that I do a lot. Like when I write sine and cosine, I tend to forget the arguments, but that's not very good when your sines and cosines use different arguments. So if you have a t in one cosine and a phi in the other, then this is very counterproductive. But yeah, let's go on. So we have cosine squared t plus sine squared t plus 2 sine t cosine of t. And then we keep on multiplying, and we will get another cosine squared of t plus a sine squared of t minus 2 sine t cosine t. So the cool thing about those parts here is they cancel each other out because it's plus and minus. And the other cool thing that we will see is cosine squared plus sine squared. This is 1. Here we also have cosine squared plus sine squared. This is 1. So what we will get in the end is minus 2s. So this is the Jacobian determinant. If we plug that into the integral, then we take, of course, the absolute value. So we take 2s. So let's do that now. Let's plug that into our integral. So our integral was, first of all, x squared plus y squared smaller than 2. We have the arctan of x minus y divided by x plus y, and dx and dy are our integration variables. And now we plug in our formula, our substitution or our change of coordinates. So we will see that the x minus y divided by x plus y turns into a tangent of t. So this will become double integral. We will take a look at the limits of the integral in a moment. So we have arctan of tangents of t. Then we take the absolute value of the Jacobian determinant, which is 2s. So here we have times 2s and then times ds and dt. So this is our integral. Now we have to take a look at the limits of the integral. So what are the limits that we need here? Well, first of all, we know that t is in the interval between 0 and 2 pi because we're talking about sines and cosines. So we can say that for t we have t equals 0 up to t equals 2 pi. So what about the s limit? So what we do about that? So we know that x squared plus y squared is supposed to be smaller or equal than 2. So now we plug in what we got for x. So we have x above here is s times cosine of t plus sine of t. So we have s squared times cosine of t plus sine of t in brackets squared. And then we plug in the y, which is s squared, like the x, but just with a minus. So we have cosine of t minus sine of t and the whole thing squared, and that should be smaller or equal than 2. Now we just use the binomial formulas to calculate that, and what we will get now is that 2s squared should be smaller or equal than 2. Let's put that arrow here. And this, on the other hand, means that s squared is smaller or equal than 1. So this leads to s being smaller or equal than 1 as well. So the limits of our integral will be from 0 to 1. So our whole integral changed now to from 0 to 2 pi, from 0 to 1 over 2 st ds dt. Alright, we're almost finished. It's amazing. So let's keep on going. What we're gonna do is first we integrate with respect to t. So what we will get is, like, let's extract the 2 out of the integral. Then we have 2 squared divided by 2 evaluated at the limits 2 pi and 0, and we have s squared divided by 2 evaluated at the limits 1 and 0. So if we evaluate like t squared at the limits, then we have 4 pi squared. So what we will get is 2 times 4 pi squared divided by 2. When we plug in 0, we will get 0. The same goes for this part here. So here we only get s squared divided by 2. S squared, we plug in 1, so we will have 1/2. So what we will get is times 1/2. And this is quite simple. So this 2 equals out. This 2 cancels each other 2. So what we will get is 2 pi squared. I think that's an amazing result for an integral, and I really loved solving it. I hope you loved it as much as I did. Let me know in the comment section if you found a better solution. You guys sometimes tend to find very nice and very easy solutions. I really like it. I can still learn a lot from you, and I love the whole communication. So yeah, leave me a comment. Also leave a like if you like this video, would be nice. Hit the subscribe button. I know you guys probably don't like hearing this, but it really helps me a lot. And yeah, until the next video, my fellow path integrators, bye!